Hi, we are Team 5. Our team has three members, Jinyoung Kim, Sunghoon Kim, Jungwoo Chu. We chose search on the replay buffer, bridging, planning, and reinforcement learning. This introduces fresh methods for goal-reaching tasks. These methods can obtain policies that generalize substantially better than the others, learned directly from reinforced learning. Let's start. Searching on replay buffer is a machine learning algorithm. This learns to make decisions to reach goals. Typically, this sort of control algorithm rely on planning methods and reinforcement learning methods. Both have limitations. Planning algorithm can reason over long horizons, but cannot deal with high-dimensional observations. Reinforcement learning algorithm fails to plan over long distance. Searching on the replay buffer attempts to combine the best of both algorithms. Then, what is search on replay buffer? Look at the A. Standard goal conditioned reinforcement learning fails to reach distance goal. And look at the B and C. The agents observes in replay buffer as waypoint leading to the goals by using the agent's value function. And D. Agents can run uh, graph search to find the sequence of waypoints and then use goal conditions policy to reach each waypoint. Here is algorithm summary. The algorithm combined with graph search and goal conditioned RL. This starts by using graph search to obtain the shortest path from current state to the goal state, planning over the state in replay buffer. This estimates the distance from the current state to the first waypoint, as well as the distance from the current state to the goal. In most cases, this conditions the policy on first waypoint. But if the goal state is closer than the next waypoint, and the goal state is not far away, then this directly conditions the policy on the final goal. If the play buffer is empty or there is not a path to the goal, this runs standard goal conditioned reinforcement learning. In this paper, there are two experiments. First is the 2D navigation. The start and goal state are chosen randomly in free space, and reaching the goal takes over 100 steps, even for the optimal policy. This uses goal conditioned reinforcement learning to learn a policy for each environment. And this picture compare rollout from the goal conditioned policy and the search policy that I mentioned in previous slide. Goal conditioned policy fails to reach distance goal, but search policy takes action that temporarily lead away from the goal, so the agent can reach through the hallway to eventually reach the goal. A second experiment is visual navigation. It has high dimensional observation in visual navigation task. The agents receive RGB and depth images and take action to move north, south, east, west. The agent can reach the goal like 2D navigation experiments.
Okay, I will introduce the related work on this paper. And this paper is published on the newest last year, so we can say that it's a state of art on this, like combining goal conditioned topologies and planning with the RL. And I will introduce four areas that related to this work. First one is planning algorithm, and it is very well known in the motion planning and also within the robotics research, and it efficiently solve long horizon tasks, including those RL algorithm, and it works in the three steps. First is efficiently sample the valid states, and then it estimate the distance between two states and it require the local police to reaching nearby states. And next one is goal condition RL. And this policy takes input the current state and the goal state, and it predicts the sequence of actions to arrive the goal. And recent algorithms are combining all policy algorithms with the goal labeling to improve the sample complexity and robustness of the goal conditions policies. Next one is Hierarchical RL, and it automatically learns a set of primitive skills to help an agent learn complex tasks. And it has two different classes of the method. And first one is jointly learn a low-level policy for the performing each of the skills together. And with the high-level policy for the skills, sequencing these skills to complete the desired task. And another class algorithm focus solely on automatically discovering these skills or sub-goals. The last one is model-based RL, and it has approached all perform some degree of planning, from predicting the value of the sum state, obtaining representation by unrolling learn dynamic model, which we learn in our classes, and or it learned the policy directly on the learn dynamic model that, as I said before. And it also has two different line of works. First one is embedding the differentiable planner inside a policy, which the planner can learn end-to-end network because it is differentiable with the rest of the policy. And the other one is explicitly learns a representation for use inside a standard planning algorithm. And this paper sharing the code on the Google Colab style, and it also has the great visualization tools as you saw in the introduction of this paper. And we will test this code. We will like replicate this code, and we will test our hypothesis that whether it is good or better.
Hi, this is the third presenter, Song Kim. Here's our suggested improvement methods and plans. We plan to use A-star algorithm instead of Dijkstra's algorithm for path planning and ensemble value functions with different maxes. Let's talk about using A-star algorithm first. A-star algorithm is one of the graph search algorithm, and it chooses which node to explore next according to the value of F3, which is the summation of H3 and G3, where H3 is the heuristic function that estimates the cost of the cheapest path from node 3 to the goal, and G3 is the cost of the path from the start node to node 3. And as you notice, without H3, A-star algorithm becomes Dijkstra's algorithm. And if the heuristic function H3 is admissible, A-star algorithm is guaranteed to return a shortest path from start to goal. Here's the example of Dijkstra's algorithm and A-star algorithm. As you can see, by utilizing heuristic function H3, A-star algorithm finds the shortest path much faster than Dijkstra's algorithm. Thinking about our value function, it gives the information of list cost from current state 3 to goal state. Therefore, we can utilize value function for H3, making it improves to look for a better path by using A-star algorithm. Our second plan is the ensemble value function, which comes from different hyperparameter maxdist. Approximating Q function with DNN may lead the value function suboptimal. And under this suboptimal value function, shortest path with too many waypoints becomes more noisy. And above figure in this slide shows policy without waypoints. You can see that it takes a huge step but fails to reach the goal. On the other hand, with dense waypoints shown in below figure, it successfully reaches the goal but moves with lots of noise. And recall the role of maxdist. When maxdist is small, it constructs a stable graph and makes dense waypoints. However, it is hard to find the path to the goal state with small maxdist. On the other hand, when maxdist is large, the probability of underestimating the distance between pairs of states increases. However, it becomes unstable as it underestimates the distance. To compromise it, we plan to use the ensemble of value function with different maxdist. We expect that ensembleIt will give sparse waypoints for simple path and dense waypoints for complex path. Here's the end of our presentation. Thank you.